Hello, my name is Robert Smith and I'm with New River Community College, and today we're looking at how to calculate the change in Gibbs free energy at standard state for a reaction. And it's very similar to the video that I did on calculating the entropy change in a reaction, except we're using the values for the Gibbs free energy of formation for each species, which you can get in the back of your textbook if you're using Chemistry by Chang, and that would be in the appendix, or you can acquire it online or by whatever resource you have. It's actually a little bit easier given the problems that I've provided, because the Gibbs free energy of formation for species that naturally form at the state in which we're providing will have a Gibbs free energy of 0. So in the case of liquid mercury, you have a Gibbs free energy of 0. Same thing with diatomic oxygen, same thing with nitrogen, and same thing with hydrogen. So really all we're worried about is that the Gibbs free energy, delta G, at standard state for the reaction is going to be the sum of the coefficient times the delta G of formation at standard state for the products, minus that same summation. Again, we'll do it in J, C sub J, delta G of formation, standard state, for reactants. In this case, our products are 0. So we're starting with delta G. In the first case, delta G of the reaction is equal to 0 minus 2, because of the coefficient 2, times the delta G of formation for mercury oxide, mercury 2 oxide, which in this case is negative 58.5 kilojoules per mole. So that would provide a delta G of reaction of positive 117 kilojoules per mole. Had we used species that didn't have 0 for their delta G of formation, you would use those values instead. Similarly, with the second reaction, we have delta G of the reaction at standard state is equal to 2 times the product, which for ammonia is negative 16.6, minus the reactants, which are 0. So we have a negative 33.2 kilojoules per mole. Now, the reason I chose these is so that they definitively illustrate that one has a our delta G of reaction is decreasing and one is increasing. It's positive, 117 kilojoules per mole versus negative 33.2 kilojoules per mole. If your delta G is positive, that means that the reaction as written in the standard state, using the temperature provided of 25 degrees Celsius and at 1 atmosphere of pressure, is not a spontaneous reaction, which means that we would have to do something to make this reaction go. It would not, at 25 degrees Celsius and at 1 atmosphere of pressure, it would not go in the direction of degrading mercury 2 oxide down to mercury and oxygen. That wouldn't spontaneously happen. However, because this second one is negative, we can say that if you had nitrogen gas and hydrogen gas in these proportions, you would produce ammonia gas spontaneously or seemingly spontaneously. The reaction would just proceed forward at 25 degrees Celsius and 1 atmosphere. But again, the big takeaway on this, beyond just the assessment of the sign on delta G, is that the calculation of delta G is very similar to the calculation of delta S, and also delta H and all the other ones that we've done in the past.